By every reasonable rule astronomers currently understand about how stars die, this planet should not exist. Its star did not simply age quietly and fade away. It swelled into a red giant, ballooning outward to a size large enough to have physically engulfed and vaporized anything orbiting anywhere near its current position, before finally collapsing down into the dense, burned-out stellar corpse astronomers call a white dwarf. And yet, orbiting that same white dwarf today, closer to it than Mercury orbits our own sun, sits a planet roughly the size of Jupiter, fully intact, carrying a genuine, detectable atmosphere. When the James Webb Space Telescope finally got a clear enough look to actually study it directly, what it found did not simply confirm that this impossible-seeming survivor was real. It revealed the planet is considerably hotter than it has any right to be, a specific, measurable clue that has now allowed scientists to reconstruct exactly how a world this close to a dead star actually managed to survive its own sun's death at all. This is the real story of WD 1856b, and what its survival reveals about the eventual, distant fate awaiting planets like Jupiter and Saturn, long after our own sun eventually dies. To understand why this specific planet's mere existence puzzled astronomers so deeply, you first need to understand exactly what happens when a star similar to our own sun finally reaches the end of its life. Billions of years from now, our own sun will exhaust the hydrogen fuel powering it, and in response, its outer layers will begin expanding dramatically, swelling outward into what astronomers call a red giant, a star potentially large enough to expand well past Earth's own current orbit, engulfing Mercury and Venus entirely and quite possibly consuming Earth itself in the process. Eventually, that same red giant sheds its outer layers entirely, leaving behind only its small, incredibly dense core, a white dwarf, an object often comparable in size to Earth despite still carrying a mass close to that of the original star. Any planet that happened to be orbiting anywhere close to that star during its red giant phase faces almost certain destruction, either directly engulfed by the expanding star itself or torn apart afterward by the star's own powerful, concentrated gravity if it strays too close to the newly formed stellar remnant. WD 1856. B, first discovered back in 2020 using NASA's Transiting Exoplanet Survey Satellite and the now retired Spitzer Space Telescope, immediately presented astronomers with exactly this kind of puzzle. The planet, roughly the size of Jupiter, orbits a white dwarf named WD 1856 plus 534, sitting approximately 80 light-years from Earth, completing a full orbit in just 34 hours, at a distance less than 2 million miles, more than 50 times closer than Earth orbits our own sun. Andrew Vandenberg, an astronomer at the University of Wisconsin-Madison who worked on the planet's original discovery, summarized the core mystery directly and plainly, explaining that WD 1856b somehow got very close to its white dwarf and managed to stay in one piece, despite the fact that the white dwarf creation process itself destroys nearby planets, and anything that later strays too close afterward is usually torn apart by the star's own immense concentrated gravity. For years following that initial discovery, WD 1856b remained a confirmed, genuinely puzzling anomaly, its mere existence firmly established, but the specific mechanism explaining exactly how it had managed to survive remaining entirely unresolved. That finally changed this year when an international team of astronomers, in research published in the journal Nature on July 1, 2026, used the James Webb Space Telescope to observe the planet during a genuine transit, watching it pass directly in front of its host star from Earth's own vantage point. This was, in itself, a genuinely difficult technical achievement. White dwarfs are extraordinarily dim compared to ordinary stars, and due to this, 1856b only actually crosses in front of its star for a brief window lasting roughly 8 minutes at a time. Victoria Boehm, an astronomer at Cornell University who co-authored the study, described the challenge involved in blunt, practical terms, explaining simply that if you blink, you miss it. A genuine technical constraint the research team had to carefully plan their entire observing strategy around. Watching that brief transit unfold through Webb's instruments allowed researchers to measure the planet's properties with a level of precision no previous instrument had achieved, establishing a mass somewhere between 4 and 11 times that of Jupiter, and for the first time ever directly detecting a genuine atmosphere surrounding a planet transiting a dead star, the very first observation of its kind in the history of astronomy. Ryan MacDonald of the University of St. Andrews in the United Kingdom, the study's lead author, offered a striking way to visualize the specific geometry involved, explaining that the planet is about the size of Jupiter, while the white dwarf it orbits is only about the size of Earth, meaning the planet itself is roughly 7 times larger than the entire star it circles, a genuinely strange, almost inverted relationship compared to every planet orbiting a normal, active star. The atmosphere Webb detected turned out to be genuinely rich in chemical detail, containing methane along with various aerosols and organic compounds, a composition researchers noted would likely give the planet a color and general appearance broadly similar to Titan, Saturn's own large, hazy orange moon. But the single most important piece of information Webb's observation actually provided was not the atmosphere's specific chemical makeup, it was the planet's temperature. Webb's instruments measured WD 1856 ZU at approximately 260 degrees Fahrenheit, a reading that immediately stood out as significant, since it came in roughly 240 degrees hotter than the planet should have measured if the faint residual glow of its dim, dying host star were its only genuine source of heat. This specific, carefully measured excess heat became the crucial clue researchers needed to finally reconstruct the planet's actual history. Christopher O'Connor of Northwestern University, another member of the research team, explained that this discovery essentially narrowed the mystery down to two competing possible explanations for how the planet ended up in its current, seemingly impossible position. Either the host star's original red giant expansion phase was somehow less extensive or less destructive than existing models generally predict, allowing the planet to survive in a comparatively close orbit throughout that entire dangerous period, or in the considerably more likely scenario the excess heat measurement actually supports, the planet originally formed and spent most of its early existence considerably farther from its star, safely outside the reach of the star's later red giant expansion, before migrating dramatically inward sometime after the white dwarf had already fully formed. That second scenario, planetary migration occurring after the star's death rather than survival throughout the star's most destructive phase, fits considerably better with the specific temperature Webb actually measured. A planet that had spent billions of years sitting in a tight, stable orbit since the earliest days of its star system would have had ample time to fully cool down to match the white dwarf's own faint residual glow. A planet that instead migrated inward relatively recently, on a timescale short compared to the system's overall age, would still be, carrying leftover internal heat from its own formation, exactly the kind of measurable excess warmth Webb's observation actually detected. Researchers have proposed that gravitational interactions with another, still undetected object within the same system, potentially another planet or a companion star, could have gradually destabilized WD 1856b's original, safer orbit long after the central star had already become a white dwarf, sending it spiraling inward to its current, tight 34-hour orbit only comparatively recently in the system's overall multi-billion-year history. It is worth pausing to appreciate exactly why this discovery carries genuine significance well beyond simply resolving one specific planet's own individual puzzle. Researchers studying WD 1856b have been explicit that this system offers something genuinely rare and valuable, a direct physical window into the actual future fate, awaiting planets like Jupiter and Saturn within our own solar system, once our own sun eventually reaches the end of its own life billions of years from now. Scientists currently know with reasonable confidence that our sun's eventual red giant phase will engulf Mercury, Venus, and quite possibly Earth itself. What remains considerably less certain is whether our solar system's more distant gas giants, Jupiter and Saturn, will survive that same process intact, continuing to orbit whatever remains of our sun long after it has collapsed into its own eventual white dwarf, WD 1856. B represents direct observational evidence that at least some giant planets can survive this kind of stellar death and continue existing afterward, offering researchers a genuine physical case study for understanding exactly what that distant future might actually look like for worlds like our own outer planets. It is worth being precise and honest about exactly what remains uncertain here, since that precision is exactly what separates genuine scientific progress from an overstated, prematurely declared solution. Researchers have not yet definitively confirmed which of the two competing explanations, an unusually mild red giant phase or a later gravitational migration, ultimately accounts for WD 1856b survival, though the specific temperature evidence Webb gathered points meaningfully toward the migration scenario as the more likely explanation. Confirming this conclusion with full certainty will likely require additional observations, potentially searching for the specific undetected companion object researchers suspect may have originally triggered the planet's inward migration in the first place. Step back and consider what this entire discovery actually represents. About the value of directly observing systems that have already reached a stage of stellar evolution, our own solar system will not experience for billions of years. WD 1856b is not simply an interesting isolated anomaly. It is a genuine physical preview of a specific, distant chapter in our own solar system's eventual future, observed directly, in real time, rather than left as pure theoretical speculation. Webb's ability to actually detect and characterize a genuine atmosphere on a planet transiting a dead star for the first time in the history of astronomy demonstrates exactly the kind of previously unreachable scientific territory. This telescope continues to open up, transforming what would have remained an unresolved, purely theoretical puzzle into a genuine, evidence-based reconstruction of one planet's own improbable billions of years long survival story. So here is the honest, complete picture behind why the specific planet genuinely should not exist, and yet clearly, undeniably does. A world roughly the size of Jupiter orbits the collapsed, Earth-sized remnant of its own long-dead sun, closer than Mercury, orbits our own star, having somehow survived a stellar death process that, by every conventional model, should have destroyed it entirely. James Webb's detailed observation of that planet's transit revealed not just a genuine, chemically rich atmosphere, the first ever detected on a world orbiting a dead star, but a specific, telling excess of heat that now allows scientists to reconstruct the most likely explanation for its survival, a planet that spent most of its existence safely distant from its star, only migrating inward to its current, precarious position some time after the star's own destructive red giant phase had already safely passed. If you want to see what Webb reveals next about the eventual fate awaiting planets like our own solar system's Jupiter and Saturn, subscribe and turn on notifications, because this single improbable survivor may be showing us exactly what our own solar system's distant future actually looks like.